how do you teach periodic trends? Are you teaching the trend as a package deal, or are you focusing on each individual attribute, each individual property of atoms? In this video, I'm going to share with you my lesson on ionization energy, the periodic trend. If you've been around here for a little while, you might have seen my other periodic trend video, the one focused solely on atomic radius, because yes, I go separate. I do it differently. I don't teach them as a package deal because it's not really all about the periodic trend. Especially if you're working in the NGSS standards or some state adaptation of that. Your goal, your standard, is to, yes, use the periodic table as a model. But the focus is on predicting properties based on patterns of electrons. It's not all about the pattern within the periodic table. And so just the standard itself is an argument for separating them. Here at Lab and Every Lesson, what I try to inspire science teachers to do is go discovery-based, go inquiry-based each and every day, training your students to dig in for themselves and uncover, reveal the core ideas that you need them to learn. Of course, your role is still super important, but instead of just trying to passively transfer the knowledge, it's all about you guiding and supporting and shepherding, and that's how we can really take our classrooms from you being the end-all be-all, when you're out for a day, everything implodes, to students really running the classroom. It's an entirely different culture shift. So I'm so glad that you're here to join me. Before I show you this lesson today, and the way I start all of my videos is really to give you some context to the bigger picture. So in this lesson, ions and ionization energy, it's really important to highlight that I am nearing the end of my content unit, my standard-based content unit on really all electrons, that entire piece that is the pattern of electrons and outermost energy levels. We start with the basic modeling of atoms with Bohr and with Schrödinger, with box diagrams and electron configurations. We use them to argue size and also patterns in the table for electron configurations, leading to the octet rule. And then the outcome of the octet rule, which can be predicting charges, of course, if electrons are transferring. At this point, I haven't talked anything about electron sharing yet. What we're really doing is setting up the students to argue for bonding one way or another in time. Now, when I teach the ion and ionization energy lesson, the periodic trend in ionization energy lesson, I'm coming immediately off of predicting ion charges. So what we're doing here is we're playing off of really still springboarding from the octet rule, where I had to take some liberties in that lesson. That time I had to sort of just tell my students, nature's lazy. It would rather do one thing than six things if it came down to losing an electron or gaining six. So I really focused on the energy component of it, but I didn't give them any actual data. No energy data. This is the lesson where we get that energy data. We really get to say, this is why our metals lose electrons. And this is why our nonmetals don't lose electrons, because there is an energy barrier to doing that. And it really becomes further evidence to support predictions that I've already taught them to make in the octet rule. It's also important to note that this is not the last in my series, but almost. The last in this series of lessons is the periodic law. And now this lesson itself doesn't hugely contribute to that periodic law lesson, but in that periodic law lesson, which is the next video I will post, it really hinges entirely on students reviewing what they know about everything we can get from the periodic table to expose the similarities between elements and groups. And that's how we do learning here at Lab and Every Lesson. It's really about our job becomes so hyper specific to our content knowledge and our content mastery, and using that to craft experiences, not just lessons, but experiences for our students. What we're also looking at here in this worksheet is the breakdown of science and engineering practices, which are laid out by the NGSS. And in Pennsylvania, I work with the STEEL standards, and the cross-cutting concepts of science that are laid out there. Now, if you're a secondary science teacher and you're just watching to see what you can glean from this lesson, or you don't use the NGSS standards, you're not bound to following them, still trying to do so will bring life to your lessons. Focusing on incorporating these pieces will make walking away from lecture or just letting go the safety net of lecture so much easier. Because the premise of active learning and inquiry-based learning is that the students are doing, but you are their guide. And so this is your playbook. This is your playbook. In this lesson in particular, ionization energy, periodic trends in ionization energy, my students are developing and using models, not of atoms though. Pretty much throughout this entire other unit, we're focusing on the model of the atom. And we will use that in this lesson to argue the reason why. So arguing from evidence is pretty much a standard go-to across all of my lessons, is a goal that I have for my students. But rather using the periodic table as a model. So anytime we have a periodic trend lesson focus, it's periodic table as a model, right? So that's where we're using the model here, but really honing in on quantitative data in this lesson. So analyzing, interpreting data that students obtain themselves, that students evaluate themselves, and that students communicate back to everyone themselves. These are key science practices. And when they do those things, we are going for a lot of cross-cutting concepts here. When we are working in this lesson, the things that we can highlight as teachers, and certainly in the design of this lesson, making sure those themes are coming through, that the pattern exists inside the periodic table. That in terms of cause and effect, ionization energy is what's required for those electrons to jump out. There is some action that's happening, and the cause is the energy we zap the atom with, right? So, I mean, that's like an underlying, it's not necessarily at the forefront here, but it's playing in the background. Students need to realize this is not just something, this is an event that could potentially happen. And will it happen based on scale, proportion, and quantity? Scale, proportion, and quantity relating to what? Well, firstly, the number of electrons in the orbitals, and why or how many will jump out, because ionization energy is all about electrons taking a hike, right? But also in the quantity or the scale of the energy that's applied, one relative to another. And that's where our system and system models come in, because we are going to refer back to those Bohr models, to those distances from the nucleus, to the number of protons inside the nucleus, to rationalize and explain why some electrons hold on for dear life and others, the nucleus is like, I didn't even notice you were gone. Energy and matter. Obviously, when we're talking about energy, the lesson itself, the core idea itself has energy in the title. We're dealing with energy, right? And matter as an idea that's happening. And stability and change. That lesser energy required for this process to happen, for an electron to get pulled off of an atom, would mean it's more favorable. So really touching on that as well. The only cross-cutting concept really not addressed here is structure and function. And I personally don't highlight or encourage or emphasize that here because I haven't yet launched into bonding. Now, if you're teaching this lesson in the context of ionic bonding, then absolutely. Then you're going to emphasize and you're going to tweak things a little bit to make sure that students are aware that when that electron comes off, it's going to another atom. And there is a cause and effect with that relationship as well. So I believe that some of our cross-cutting concepts either shine through or don't based on the bigger context we're giving them. And you can definitely tweak that in your learning intentions for the lesson. Before I quickly jump into that tidbit of knowledge, I want to let you know you can download this worksheet, which outlines my approach to satisfying this structure and properties of matter standard strand in the NGSS. The link is in the description below. As to learning intentions and tweaking those are one of 5 components in a framework I have for lesson planning. And if you've watched a video on my channel before, you've heard of it before. I've said it a whole lot of times now, but for anybody who may be new that's watching, I'm going to go through them even again. First, review and preview. It's a warm-up, it's a bell ringer. What it does is it causes students to activate what they already know, maybe not academic even, maybe life experience based, and integrate it to what's coming down the pike in the lesson for the day. So it's not just some random activation. It's not like a word search or a word find. It's not to jog your memory with vocabulary. It's like you're in it. It extends. Your lesson is going to extend that warm up so that honestly, sometimes by the time I'm done with review and preview, my students have half the lesson. They've got half the core idea. It doesn't work that way always, but a lot of the times it does. Learning objective, expressed as learning intentions and success criteria, they help us separate the why and the what from the how. So our learning intentions going to be real specific about why bother? Because students always want to know that, right? Why bother learn this? Well, in chemistry and in any very cumulative subject, the content links together and it builds. And so usually there's a bigger reason, really for every single lesson in this series I've just been talking about, it's the same learning intention, and that is to get us to the rationale, the explanation for bonding and for chemical change, and the prediction to be able to make predictions in that context. Success criteria, though, those are things that students can actually use to check off throughout class as they're completing activities, monitor their own engagement, be done with a day and look back on what they did, or be done with a whole unit or whole month and look back at this list of all that they've accomplished. In fact, my success criteria allow me to copy and paste at the end of a unit all the things the students should be able to do and prove to them they have done come test time. But then there's also assessment-specific success criteria, where in a class like mine, like chemistry, students have to be able to complete a standardized style exam, in addition to the deep thinking stuff. And when I first devised this framework, it was really important to me because I wasn't totally sure that the activity I had designed would connect in that way, that students would be able to see it through and sort it out. And if nothing else, it allows me, it's a bullet point there for me to go, this is what they need to be able to do, make sure it happens. But most importantly, when you give students success criteria and they have it as a means of tracking their own learning, you are one step closer to student-centered and really giving those learning skills that will last a lifetime, that will teach them through modeling how we track our progress, how we set our goals, how we fulfill our goals. Then we have always an activity. I am the active learning, inquiry-based secondary science, student-centered secondary science teacher. So we need an activity. A lot of my activities are simulation-driven, but when I can't find a simulation, I go with an interactive tutorial or a video or a text. There's always something students are doing, and they're not doing it because I showed them how. They're not doing it because they need practice. They're doing it to unearth the main idea because is no lecture happening here. As part of that activity, there is a data-dependent analysis. There is a look at either qualitative observations or quantitative numbers that allow students to find patterns and to use math concepts to, do anything in that science and engineering practice realm. Analyze and interpret data, construct explanations, design solutions, ask more questions, or further define a problem. It's where the magic happens, really. And typically I'm leading students through that as a together activity. And then at the end, we do the skill practice that makes sure it's all tied to that assessment specific success criteria and making sure our students are going to achieve. They're not just engaged, it matters, and they're going to learn the thing they need. The review and preview for this lesson, ionization energy, ties directly to the lesson I have taught before it, the day before. So asking students here to use the periodic table to determine the charge on an element when it ionizes. They've got 6 examples here. 3 of them are metals, 3 of them are non-metals, making sure we share the love with the cations and anions alike. If you haven't watched that video, please do take a peek at that, because that lesson provided multiple ways for students to get to this information. We heavily used models to make the math more palatable, but then gave 2 options for determining charge using simple math, addition and subtraction. And also that periodic table hack, which is really what I'm wanting students to do here, because one of our learning intentions throughout is to always be able to go to the periodic table, do it quickly and easily, even though we have a toolbox full of models we could pull out and draw if we need to. So you can see here, totally equipping them. Maybe they were absent the day before. Maybe this is where you're going to capture that student who missed class yesterday. Maybe they were involved in some club or group, or they were dismissed early and they missed your class. Whatever the case might be, and they're not quite sure yet. They've not caught up on what you did, but they get a great snapshot here, and they can maybe work with a partner to help them sort through. You know, your high achieving students will get it just from this simple 5, 10, 15-minute activity. But for your struggling learners or your average student, honestly, they just need more practice with this, and you haven't waited to the end of the week to give a homework, or you didn't give this as homework because you know there's a whole lot going on with your students and maybe term papers they have to write and different things they have to do. So you're giving this practice in the now when you're there to support them, when they can get explanation after explanation and you go over it. And you have the ability to do that here. Also, this is designed so that students can use what they know to determine what they don't know. So they truly don't even have to lean completely on the periodic table hacks here or their other toolbox tools. What they can do is use the number of protons and electrons to get the ion charge, or work backwards, right? So we have some missing information here and some information that can be a key to determining if a student doesn't know how to get the total number of electrons after the octet rule has been applied, then they could take the cue from some other elements in the list. But this does kind of cue up for us patterns all over again. Periodic patterns, because when we review this, we should be able to say, hey there, group 1 elements, you're all charged +1, and so on and so forth. It reinforces that idea that our charges on ions aren't going to be any greater than 3, plus or minus, and that metals are always positive, non-metals are always negative. Learning intention success criteria as promised here. Today I'm learning about ionization energy. That's worth a quick pause to just reiterate that learning intention is the what and the why. So sometimes you'll see my learning intentions written, today I'm learning how to, because it's a very skill-based lesson. Today, my students already learned about how to apply the octet rule. Today, they're learning about the energy that's required. So it's just a shout out there. Your words matter. Always talk like a scientist. That goes to our disciplinary literacy skills, the reading and writing of some of these higher level sciences, because they need to understand you. We need to understand them, right? Using the pattern observed throughout the periodic table to predict the likelihood of chemical change and explain how and why atoms will undergo change through bonding. Again, that's the through line for the entire unit, because that's very standard driven. That's the what we're learning. and the why. Now the how. Students, now this lesson actually looks so similar to my atomic radius lesson because we use the same simulation to gather our data. So I always write, I'll be able to define terms on the word wall. Here specifically, we're looking at the terms ion, ionization energy, and I throw out a little bit about electron affinity, even though me and my class, we don't focus on electron affinity as a trend they need to be familiar with. I honestly don't know why that is. If you know why that is, feel free to drop it in the comments below. But I've taught at the college level, I've taught at the high school level. I've never seen electron affinity be like a thing that we have students sort out. Maybe because as an extension activity, we can get to one from the other. Maybe. We want students to list the ionization energy values. So they're going to go to a place, they're going to collect values, they're going to obtain their data for elements in period 2, group 1. And then they're going to evaluate that data by annotating the actual periodic table. This is exactly what we did in the atomic radius lesson. So they build the trend for themselves. Then the sorting out, the CER style, arguing evidence. What's the claim? What's the evidence? What's the reasoning? Really leaning on that atomic size trend that we've already learned about and what we've learned about the octet rule, frankly, and the structure of atoms in general to compare the amount of energy required for atoms to lose electrons. Then go forward with this trend and use it to compare ionization energies. This is that word wall I referred to. Very, very simply, I might give this a quick 2-3 minute nod, share with students what is ionization energy, because, as terms and definitions and technical jargon goes, this is probably one of the most misunderstood by virtue of the fact that ionization as a process is the process of an atom becoming an ion, a neutral becoming a charged atom. But then we call it ionization energy, and that makes it seem like it's the energy to create any ion, cation or anion. This one is, of course, very specific to the formation of a cation, how much energy it takes to just pull electrons, which is why I always share with students there is a similar feature, a similar quantity of energy we can observe, which is called electron affinity, the energy for an atom to accept electrons, because that could be prohibitive too. But after laying that foundation, I send them back to the same interactive periodic table they used for the atomic radius lesson. And again here, task instructions, super generic. This is what I would project on the board as students are working, because the artifact outline I give them on which to collect their data, their observations, graphic organizer, if you will. You can call it a worksheet if you want to. It is usually very specific and very strategically designed to facilitate analysis, to make the patterns pop. That's what we're after today. So they're going to visit a website, compare ionization energies, record observations, and mark up the periodic table. This is what that artifact outline looks like. I know it's a lot of words here at first. Really important to just take it step by step. Excellent delivered digitally because it's a link. So, saving this slide as a PNG file, loading it as a background to a Google slide, or I really, really love and advocate the use of Seesaw in your classes, because if you use it consistently, it will give students a home for all of their science work for the entire year, and you have to do virtually nothing for that to happen. So it's win-win. Plus, their families can see their progress if you want them to. If you want to know more about Seesaw, I also have a link down below to my EdTech Essentials guide, and you can download that too. It's super comprehensive. It'll help you get started right away with an activity like this, loading it in, creating an account, doing the whole thing. But I digress. Here, again, there are places for students to record the energy number in kilojoules per mole for lithium versus the 4 elements below it in group 1, and lithium versus the 4 elements to the right of it in period 2. Then asking students to highlight blue or draw blue boxes around elements that have greater ionization energy than lithium, green for smaller ionization energy than lithium. So what we're doing here, folks, be clear, we're obtaining information, collecting it, we're observing, it's a science practice. We are using the periodic table as a model as we evaluate that evidence. We're looking at the numbers, we're thinking about the numbers. You might argue a little bit of math and computational thinking here. Definitely scale, proportion, quantity. And creating evidence. We're actually creating evidence by having them annotate the table. And it becomes very clear then where are the biggest energies, where are the smallest energies. Now, it's almost an extension question because your highest achieving students will have the time to consider it, but maybe in the 15 minutes or so you allow for this activity to take place, your slower students or the ones who aren't as fluent in data analysis or just move slower, do all the executive things slower, they might not get to the big question at the end, but really what we want to connect to is why. How is this evidence? Well, what does this mean? Why is this happening? And giving that prompt, this is the guided part of guided inquiry. And chemistry's tough, so inquiry-based chemistry, I highly promote guidance. Consider what you already know about size. So also what we're doing here is we're spiraling. So we're activating even more prior knowledge and pulling it in. What students can do at this point is either actually on their paper, actually on their screen, or in their mind's eye, see the atomic radius periodic trend and apply that, realizing that they're opposites and that the greater ionization energies are coming from elements that are smaller. And I'm giving them those choices. Now, this is a big part of where you can differentiate your students. You get rid of that altogether so as to quell the concerns about, oh my gosh, there's so much to do. Or take down the critical thinking. There's two ways I differentiate. I take down the critical thinking or I raise it. I take down the amount students have to do or I increase it. Another way to differentiate this lesson would be to do students partners. So that the data collection even goes faster. You can do the activity in a smaller amount of time because one student will collect the data from group one student will collect the data from period 2, and then they will put their heads together and answer that question. And everybody gets to the question, and doing it together lowers the critical thinking threshold too, right? Because you're kind of brainstorming and you're chatting about it. This is the essence of the whole lesson. This is the slide where I would prompt students to say, actually, I'd probably share my answer key. Of course, I'm watching what students are doing. There's a lot of times wherever I can, I capitalize on student work to project it and talk through it. But for this activity, there is no way anybody is answering anything different than what's seen here and having it be correct. So it might say, okay, everybody found these are our smaller elements, our smaller ionization energies. These are the greater ones. Now, not asking why, because that's the one thing you don't want to do ever. Ever. Why shuts down everything. Everything. Instead, ask, where's the evidence? What's the evidence? And so what I'm pointing to here is to cite evidence to explain why. So what do you see? The reason that helps engagement is because everyone can see. Not everyone knows. And even if they do know, they think they don't know. Or they're shy, or they're self-conscious, or there's all this stuff happening, right? But everyone can see, and everybody can say what they see. So I've added some models on the board here. Here, we are using models to argue evidence from data we collected. So many of those science practices here. Systems and system models at work. Cross-cutting concept. I can't flip my screen when I'm recording in this mode. Sometimes I need to look at the list again. Okay. Cite evidence to explain why valence electrons in big atoms escape more easily than in little atoms. So here I would simply say, what do you see in cesium versus lithium that allows that cesium electron to take a hike pretty easily? Because that's low energy. I'm drawing all my energies here in terms of higher ionization energy. So the lowest ionization energy down near francium, the highest up near fluorine. And clarifying that too, right? All these notes on the board. Ultimately, students will almost always cite the number of electrons. But, and this is a value in doing it after we've talked about atomic radius at some point. Now, this for me, this is several days, maybe more than a week, maybe 2 weeks from atomic radius. But they've already recognized that they can no longer ignore the nucleus, because the nucleus was important to size and why some atoms in the same period were smaller than others. But here, the nucleus is obviously quite different. The number of orbitals also was integral to the size, the reasoning why size obeyed this pattern within the periodic table. So it doesn't take too long for students to connect that orbitals are the culprit for low ionization energies, and protons are the culprit for high ionization energies. Because really it's the same reasoning as atomic radius. It's just an opposite trend. And that's something that we highlight. So because this has been traditionally a more challenging core idea for me to get from students in the past, I do include, if there's any place I do lecture, it's usually after we have had this discussion about our activity data. And so this is, as an extent of lecture, and maybe if students need to grab some notes, these are the ones that are important. Highlighting here, first of all, that we're only looking at the main group elements. This doesn't apply to our transition or intertransition metal elements. Focusing on the orbitals important in groups and what I like to call the proton power. And this is going to depend on you and your level of student that you work with. Certainly if you work with honors, you're probably going to talk about effective nuclear charge. You're probably going to talk about electron shielding. I simply say proton power. The amount of protons in the nucleus has the ability to create greater electrostatic attraction, period. And sometimes I'll throw in that it's like Spanx. Higher proton power is like putting on a pair of Spanx, sucks you in and it smooths you out. Because sometimes they get a little silly. I also usually throw in, because my students know about the octet rule at this point, and they've already argued the fact that nitrogen, oxygen, fluorine, they already have almost what they need for an octet. So it's like when you're saving money for something really special. And you're saving, you're almost there, and something else comes up that you want to buy. But my heart really set on this. I'm not going to let any of my money go. I'm going to just keep waiting. And these elements that are already close to their octet absolutely won't let them go. So I throw that into, again, it's sort of an optional thing. There's not a whole lot of like data building in that, but what it does is it does spiral in this idea that the octet rule leads us to the reason for bonding, the reason for reaction. And ionization energy is chemical change. So as another reason why I like to remind students. At the end, we can summarize it. And almost all of the lessons in this whole unit that I present can come down to periodic table as a model, periodic table patterns. The biggest one being metal versus non-metal. And we could break this down just like we break it down on how they ionize, lose versus gain, and plus versus minus. We're saying here ionization energy, always high for non-metals, always low for metals. And of course, this is a great opportunity to tie in all those other things we know about metals and non-metals. Because ionization energy, and this is where I remind students what it means. We might even go back to the word wall and say, remember, this is about plucking an electron away. Which atoms like to do that? And we can say, yeah, our metals, they like to lose electrons, they become positive, and so on. So it's a good overarching The idea here is even if you are leading the most heavily during this period of time you're delivering this lesson, they are still doing ample work because your leading is coming through as questions. Unless you have a really bright group and they could just tell you the whole thing, right? They could tell you the whole story. I have not had the advantage of working with really high achieving students with these lessons. And so I would venture that they need some differentiation applied to remove some of the guidance. That's all you'd have to do. Remove some of the guidance. And then they have the muse and they have the skeleton for digging up that core idea all themselves. At the end, like in every one of my lessons, I've got some skill practice. Ultimately, kids are going to hit a question on a test or homework. Which of these four has the greatest ionization energy? And do it and do it and do it again. There's 2 examples here. Oh, when I sell lessons on Teachers Pay Teachers in my store, I'm always including an exit ticket, most likely. And those exit ticket questions are in a program called Book Widgets. To give it, all you need is a link. However, you can't collect data on the back end of that program unless you have a subscription. But you can have students download the work or screenshot their answers and submit it to you some other way. So I always like to include it, even if you don't want to be a subscriber to Book Widgets. But Book Widgets is amazing. I love it. Every one of my lessons also has a Book Widget counterpart, a Book Widget sister or brother, which is the entire lesson from goals and warm-ups straight through skill practice. And it's programmed to show students the right answers as they click, as they write, so that they get that instant feedback. If, for example, they have to leave school early for a sporting event and they miss your class, but they want to stay current, it becomes their homework. And they could just follow up and iron out the details with you the next day. Or if you need to be out and you have this becomes your substitute plan. The beauty of working this consistently every day, this kind of program, is that your students are just well-versed in learning this way. And a classroom routine emerges from the framework that is in these lessons. So students know what they're going to get from phase to phase and how to walk through it themselves. Lends itself very well to this student-centered culture. Even if you love flipping your classroom, giving them what they need to know, and then having them do the thing, flipping your classroom in this way, amazing. And then your next day is spent all with the conversation of data analysis, because frankly, every student can do the observation activity. Again, they all have the peepers. They all have the eyes to get it done.